I'm trying to keep this on time. You're probably as hungry as I am, so let's see how this goes. There's a lot to talk about. MAROON-X is on the Gemini North telescopes. It's about 3 years, but it still feels like we're the new kid on the block. A status we now lost to KPF, which we will hear more about after lunch. So let me quickly run you through the instrument specs. Of course, it's a highly stabilized fibrofatty shell spectrograph that was specifically designed for EPRV observations of M dwarfs. So that set our wavelength coverage of 500 to 920 nanometers. And we captured that spectrum in 2 arms, which for more historical reasons we call blue and red, although we should have better started with VIS and NEAR or something like that. We achieve a resolving power of about 85,000 at about 8% peak throughput under median seeing conditions. And because MAROON-X is a very small instrument, we only have like 100 millimeter beam diameter on an R4. So it really looks like a toy compared to, say, KPF or even like instruments on smaller telescopes. We have to use a 3 times pupil slicer to get to that resolving power at that throughput value. So our octagonal science fiber produces a telescope pupil that is then sliced with some micro optics into 3 rectangular fibers, and that then are stacked up to form a slit. We have also a simultaneous calibration and a sky background fiber, and they are at both ends of the pseudo slit. Of course, we have an exposure meter. Currently, it's only a white light one, so non-dispersed, something that I would like to upgrade in the future. And so far, we are working with a stabilized Fabry-Perot Etalon for wavelength and drift calibration. Instrument status, MAROON-X is a visitor instrument. Gemini is interested in getting this as a facility instrument, but we are still in transition to realizing that. We installed and commissioned in late 2019. In fact, I had to miss EPRV4 because we were just shipping components to Hawaii. We started science observations in May 2020, right when the observatory came out of the COVID shutdown. And right from the start, we are fully open, or the instrument is fully open to the US community, actually through NOAA Lab, even to international PIs. If you want to learn more about how to prepare your proposals, your observations, what to expect in terms of cadence, and so on, I invite you to go and see Theo Mochnik's poster about user's guide to MAROON-X. We staff the observations, but we also provide the raw and reduced data to the community, as well as radio velocities if desired. So we have a dedicated data reduction pipeline for that. And there is a poster out there by David Casper, who walks you through the individual steps and the details what is actually happening there, including wavelength and drift calibration. And because we are the second most in-demand instrument now in Gemini North, we are a bit swamped in supporting all the observations and delivering all the data and results. So we are now working on incorporating the data reduction pipeline into Dragons, which is the Gemini observatory pipeline system. So that pipeline will be out in public domain and people can download data from the archive, reduce their own data, etc. In fact, MAROON-X is actually used by the community for a relatively broad range of exoplanet and even stellar science cases, including transmission spectroscopy and abundance measurements. Now, MAROON-X is part of the Gemini queue because Gemini is 99% queue-driven. And because we share a port with other instruments, we only get on the telescopes for about 3 campaigns per semester, each lasting about 1 to 6 weeks, typically clustered around bright time. So there is already kind of an inbuilt cadence problem here. And the other issue we are facing is that the queue mode at Gemini does not allow for flexible exposure times. The night is pre-planned with the observations in the queue. And so that means that we have to work with those fixed exposure times and not, as it is typically common for RV instruments, reach a target signal-to-noise ratio and adjust the exposure time on the fly. So that was a bit scary, but we find so far that there's no obvious radio velocity versus signal-to-noise trend. So that's gratifying. Skip this one. So the first science example has become kind of the poster child for the instrument, just because that is a star that is actually cooperating. This is a mid-M dwarf with a test discovered 1.5-day planet in orbit around this star, K amplitude of about 3.4 meters. And so our first science observations actually targeted the star over 2 weeks. And we get down to a mass measurement with a precision of better than 5%. And that shows a RMS on that fit for the red arm of about 44 centimeters and in the blue arm, 0.2 meters. In fact, if we bin the data down to 30-minute intervals, we actually see the RMS falling to about 30 centimeters per second, which is kind of the floor for this target. And that's without any modeling or detrending of stellar activity. So this is, at least for the time being, one of the most well-behaved stars overall. We've re-observed this target in 2021 and then found basically the same level of instrumental stability, same level of noise. And actually, that's kind of typical, these values, within our individual observing campaigns. So if we look at a bunch of standard stars, we typically get values well below a meter per second for the RMS. But the problem is, of course, the star itself, as we have heard many times. We had one star that looked extremely stable for quite some time in 2020. And then starting in 2021, it started to act up. So from well below a meter per second RMS, and then suddenly you see this nice sinusoidal curve, 22-day period, something like 2 meter per second K magnitude, K amplitude. That signal kind of went away in early 2022. Still a little bit more scattered, but when we went back in the summer and observed the system again, it looked exactly like in November. 22-day period, about the same amplitude, just phase shifted against the original observations. So that really shows that if we really want to understand this, we need to observe the same stars with different instruments, disentangle stellar and instrumental effects, and also understand whether there are additional planets in the systems that we haven't seen so far. So one way to addressing the latter is a system proposed by John Brewer as a paper out from 2020, a K1 star with a highly eccentric Saturn mass planet that should have cleared out all the other orbits for lower mass planets around there. And so the Express team published their results at the time, and they got down to about 58 centimeters per second. I pulled some new data from the archive, quite some time ago, get some 86 centimeters here. And our results from the last 2 years look very comparable to that, typically around the 60 centimeter per second level. So that's one of the more interesting, I would say, radio velocity standards here, although we do see a slight uptick in activity over time. Now, the extremely well-behaved short-term performance of the system, coupled with the restrictions by the block scheduling on the telescope, makes this instrument ideal for short, in-depth campaigns to measure masses of short-period planets. And so I'm just showing one actually really random example from our 30-parsec sample where we follow up test targets around M dwarfs. This is TOI 732, M4 star with 2 planets around the system, and only with 19 epochs, we get mass measurements for these 2 planets to better than 10%. And that's kind of the typical thing that we see again and again, that we need much less time to get to good masses for these systems. The project lead is our grad student, Madison Brady, and I invite you to see her talk on Thursday at 10:30 about this sample. Now, let me switch gears here a little, and instead of giving you a sales pitch on the instrument, talk about what is actually not working great. One is, because we took a very unusual approach to this and started with a commercial shell spectrograph where we were limited in how to improve its performance, we have to work with a compromised thermal mechanical stability of the instrument. And we see temperature sensitivities of up to 7 meters per second per millikelvin at some parts of the instrument. That is a factor of 100 higher than initially simulated. So we see drifts of easily 100 meters per second per night in 2020, which, by the way, is the same period of time where we got the 30 centimeters per second at the end. So calibration is really key. So this instrument requires an exquisite temperature stability and an advanced calibration scheme to reach that performance. And I invite you to come to the Building a Better Ruler Splinter session Tuesday and Thursday, where on Thursday I will talk about the, so to speak, the secret sauce in the calibration scheme to making this happen. The long-term performance is really our Achilles heel right now, both from impacts on the instrumental profile from numerous observatory level power and cooling failures that we have seen over the past. We have Stirling coolers for our CCD coolers that when you get to switch them off and on again, they impart a lot of vibrations for a few seconds, so that can lead to shifts in focus. When MAROON-X is not scheduled for observations, the fiber and the front end are removed from the telescope and brought back. It's very repeatable, but I'm still concerned that there are effects creeping in. And of course, we see chromatic etalon drifts. They're at a level where we can't really quantify them, but they're definitely there, and they're interfering with the chromatic instrument profile changes we see over time. So there are offsets between our individual observing campaigns that are not fully covered with the calibrator itself. They're typically at the order of 1 meter or 2, but they carry an uncertainty in it by itself of anywhere between 50 centimeters and 1.5 meters. So over the long term, this is the problem for recovering periods, planetary periods, longer than a couple of weeks. So one of the improvements, and there are many that we are working on, is that we will get a laser frequency comb. In fact, next week, I'm flying back to Hawaii to install that. That should help to break the degeneracy in the behavior of the etalon and the spectrograph. We are also adding a solar feed to the spectrograph, as basically it's become a standard now for EPRV instruments. And so I'm particularly excited to see how the data from that compare, for example, to simultaneously taken data with the KPF solar feed and other instruments around the globe. So with that, I leave you with a summary slide and take questions. Thank you.
Thank you, Andreas. Questions?
Congratulations, this is really impressive performance. So can you comment about telluric subtractions? Do you do any of it? I presumably you do with the red arm.
Oh, telluric. No, yeah. So yeah, we only masked the telluric lines. We went really with a fine comb through extremely high signal noise range spectra and just mask the lines. So there is an additional inbuilt improvement factor if you would really go and start to model them instead of just giving up on that spectral coverage.
Indeed, you could do better.
Yes, yes.
Forgive me if I missed this. Is there an explanation for why those thermal drifts are so much higher than what your models or your simulations suggested ahead of time? Have you tracked that down?
Yes, so it's basically because the simulation was too simplistic. So if you just look at basically a CMAX model and start to change temperatures and just look at the in-path changes, you miss basically the bulk of the instability coming in from things like tip tilt motions, clocking, etc. So for example, the simulations that have been done for KPF were much more involved in capturing all that, right? But at the end, the question is how realistic can you actually model all this when you go to these really microscopic things, right? But that really took us by surprise that there's a factor of 100. And I think we are not the only ones. I think other instruments see that as well, that the simulated performance is much better than the actual one.
Okay, I think that I would catch occasion here to stop and thank again all the speakers of the session and also the people who helped, techniques and with the microphone. So thank you again.